Good morning. My name is Christina and I'm part of the bioinformatics class at Spelman College. I'm presenting my primary research presentation. So the presented research paper I'm presenting is titled "The Premature Aging in Mice Deficient in DNA Repair and Transcription." For background information, there are DNA repair systems that function to detect DNA damage and mistakes. Detections of these DNA errors are crucial to the proper function of the body. For example, some of the DNA repair systems include the base incision repair, which repairs modifications of the DNA, transcription couple repair, which identifies lesions that hinder the transcription process, and nucleotide excision repair that repairs DNA errors that can impact the DNA helix. Errors within DNA repair systems can lead to negative physiological effects. Previous studies have shown that an accumulation of DNA mutations can lead to premature aging, for example. Also, past research has shown that mice with a proofreading deficient version of the mitochondrial DNA polymerase G accumulate mitochondrial DNA mutations and display features of accelerated aging. The accumulation of mitochondrial DNA mutations that lead to cell apoptosis or cell death could accelerate the aging process. Trichothiodystrophy, TTD, is a rare genetic disorder. It occurs when there is a defective DNA nucleotide excision repair. Symptoms of TTD include skin hyposensitivity, brittle hair, neurological dysfunction, and impaired sexual development. Nucleotide excision repair, or NER, removes helix-distorting damage, that can occur from ultraviolet lesions, oxidative damage. Xerma pigmentosum, or XP, impacts individuals who have NER defects. So it's another negative condition as with like TTD. It leads to hypersensitivity, can lead to cancer, accelerated aging of skin, neurodegeneration. There are currently 7 XP genes that we know of. XPA is used in this experiment because subjects with this condition have complete NER defection, but don't have premature aging effects. But they do age, but just not prematurely. The hypothesis presented in this paper is that the aging of TTD mice is caused by the accumulation of unrepaired DNA damage that compromises transcription, leading to functional inactivation of critical genes and enhanced apoptosis. So for this experiment, the first step was to observe the premature aging phenotype, sexual behavior, spinal cord curvature, and cachexia, which is the wasting of the body in mice with TTD. Then a test was conducted to determine if TTD aging is due to transcription independent of NER status. So this is where they crossed the TTD mice with the mice with XPA. And next was to test to determine if TTD and XPA mice are hypersensitive to oxidative stress. And this is where they exposed the mice cells to low dosages of a treatment called paraquat for 3 days. When looking at the results for the observations, the first figure shows mice. So A and C are the wild type mice, and B and D are the mice with TTD. A and B show the mice after 3 months, and already you can see that the mice have developed a slight aged appearance compared to the healthy wild type mice in picture A. And again, by picture D, which is the TTD mouse, after about 15, 16 months, you tell it's really brittle and really frail. Looking down on the next series of pictures, in picture A, you can see like an aged appearance of the mouse. Also, in picture B, picture A, you also see, signs of deep pigmentation of the hair. Also, in picture B, you see the follicle dilation in TTD mice. So the wild type picture, the follicle's pretty skinny. It looks like it can hold the hair. But TTD, because the follicle is wider, there's more likely for the hair to fall out, or just to appear like less strong. And in figure 3, you see pictures of three ovaries. The figure A is a wild-type mouse ovary, and it looks pretty large, it's normal size. Figure B shows smaller ovaries, and figure C in particular shows ovaries with like slight abnormalities. So it demonstrates that TTD does impact sexual impairment, does impair sexual development of mice. In the last figure on the bottom, you can see skeletal abnormalities. Figures A and B are the mice at 2 months, and again, A and C are the wild-type mice, and B and D are the TTD mice. In figure C and D, the mice at 14 months, and in figure D, you can definitely see an extreme curvature of the spine compared to the healthy mouse. The last picture, figure 4, it measures the mineral densities of the wild-type and TTD mice skull and vertebrates, and you can see that the densities are significantly smaller for the TTD mice. The results from the second step of the research paper, the crossing of the TTD and XPA mice, you can see in figure A the results of the lack of development, the growth development of the mice, the slight onset of osteoporosis, and also neurological abnormalities. So the mouse on the far left is a double mutated mouse, which is the smaller. The mouse in the middle is the one with, excuse me, with TTD. And then on the right, it's the XPA mouse, and you can definitely see like the with the mouse the double mutated that there that there's developmental issues. Figure B measure the body weight of the wild type TTD and XPA TTD mouse, and you can see that the mouse with the W mutation is much lower than the other mice measured. And figure C shows the histology of the wild type and W mutated mouse, and you can see how the mouse with W mutated skin has a severe dilation of the hair follicles and other deficiencies that can lead to its other abnormalities. Here are the results of the oxidative stress test. You can see that the survival, this is where they expose the mouse cells to certain treatments. So for figure A, you can see the UV sensitivity of the indicated genotypes, and the sensitivity you can see is much greater with the XPA double mutated mice and the mouse with the XPA. And figure B is the UV-induced DNA repair synthesis, and C is the recovery of the RNA synthesis after UV radiation exposure. You can see again that the mouse samples with the double mutations are much more highly impacted by the ultraviolet exposure compared to the wild-type mouse. And D, you can see the hypersensitivity of the double mutated mice cells due to oxidative damage compared to the wild type, and even just the TTD mice and the XPA mice samples as well. So just to go back briefly, you can again, you look at the overall greater sensitivities and greater damages that occurs within the double mutated mice. So in conclusion, the premature aging phenotype occurs in TTD mice. If complete NER defect leads to more severe TTD effects. Double mutated mice with a TTD and XPA gene are hypersensitive to oxidative stress, and that the DNA is more strongly associated with premature aging, and that there is a connection between DNA damage, repair, transcription in relation to premature aging. The extent of the NER defects determines the severity and rate of TDD aging symptoms. There are a few weaknesses, just a couple weaknesses in the paper. I mentioned that TDD mice develop normally until adulthood. It indicates that TDD doesn't cause abrupt development or natural acceleration until adulthood. So while the paper talks about premature aging a lot, the mouse really doesn't prematurely age until it reaches a certain stage or prior to that. It has to reach the adult stage before it really starts to show it's prematurely aging. Also, the paper mentioned that there are other forms of gene inactivation or cell death that can lead to accelerated aging. So the paper really doesn't indicate the proportion of aging that's solely due to the DNA damage described in the paper. So that's something that would be interesting to know. Like out of all the types of reasons for aging, which one is due to how much of it is due to DNA damage. So for future directions, it could be to look into how using this model with TDD mice for future exploration of the molecular basis of aging. So that'll be something to look forward to in the future. Thank you for listening to my presentation, and here are my references.